Okay, so we've seen process coordination. We've seen the basic semantics of wait, notify, synchronized. And here we're going to look at an application of these semantics so that we understand how these mechanisms work, and more important, when to use them. Okay, that is often a bigger challenge than how these mechanisms work. Okay. And to motivate the problem we're going to look at, the application we're going to look at, I'm going to again compare the observer pattern with threads. We've done a comparison earlier once. Okay. And we saw that in both cases, there are UPCALLS involved. Okay. In the thread implementation, there's an UPCALL to the method that's forked in a thread. Okay. You make a down call first to go and create a thread object and say, please invoke this particular method in a thread. And then that method gets invoked in a thread. In the observable pattern, again, there's an UPCALL. Okay. The registrar first goes and registers in a down call an object whose method is to be called in an UPCALL, and then that method is called when the notification event occurs. Okay. So we've seen at some level of abstraction there's a commonality there. There's a notion of layering, and there's a notion of down calls and UPCALLs and callbacks. Okay. UPCALLs that are registered in through down calls are callbacks. So now that we understood, we've done thread coordination, can we find other commonalities between these two concepts? Okay, and typically one concept is taught in software engineering classes, one is taught in operating system classes, and nobody ever compares them. Okay, so let's see whether there's something interesting we can learn by trying to compare them. Okay, and so in particular, what is anything we've seen in the thread coordination section that is similar to something we've seen in the observer pattern. Okay, and even more particularly, is there a term that we have used in both contexts? Okay. Okay. So we use the word notification in both the observer pattern and in coordination. Okay. And just to sort of again to make this comparison in more depth, let's take examples to go and see these concepts concretely and understand them better. So if you do a set input string, as you did in your assignment and in the examples we saw earlier, the input string variable in some object changes. So that is an observable object. It creates an event to describe the change, and then notifies all listeners about the change. What does notifying all listeners really mean? It means calling a particular method in each listener or in each observer, and that method could be simple or it could be complex. And in your assignment 1, it was a very simple method that just printed out the event it got. Okay, and how did the observable know about the observers? It defined an observer registration method, which could have any syntax, and in our example, it's add property change listener. And so that was the down call, and so you can make it. So that's a method it defined, and either the observer or the observable or some other piece of code could go and actually connect, could actually go and make the down call to register the UPCALL. Okay, so that's our notification in the context of the observable pattern. And let's look at the lock example to show the notification in the case of thread coordination. So we have a lock object with some state, locked. Okay, it has a getLock method, and this method checks the lock condition, and if the condition is false, then it goes and sets lock to true, otherwise it waits. Okay, and the release lock goes and just sets lock to false and notifies any waiting method on getLock that locked is now false. Okay, and the first waiting method can then go and recheck the lock condition and hopefully not wait. Okay, so I've taken two examples here, and we see that one notify means that a change observable notifies when an event is sent to all observers, and one notify unblocks a waiting thread. Okay, so we understand exactly what these two notifies do. So let's go and now ask the question. Yes, we use the word notify in both contexts. We know what these notify means. And in English, often a word means different things. So just because we use the word notify doesn't mean there's any underlying similarity in the two cases. But I'm hinting there is. Okay? So the title of the slide deck was producer consumer. So somehow the concept of producer and consumer permeates both concepts. Okay. So the notified observer learns about event that caused the notification in the observer pattern, right? The unblocked waiting thread learns about event that caused the notify. Okay. Now, one of you said that, look, in the case of wait notify, you have to check the condition. You have a condition to be checked. Actually, even in the observer-observable context, the observer can check the notified state and see whether it really has to do something or not. In fact, the reason you go and pass the old value and the new value is so that the notified observer can compare the two values and see whether it needs to do any action. If the two values are so close to each other that you don't need to go and redraw something that is expensive, maybe you won't redraw. Okay, so you can argue that the condition is checked can be checked in both cases. Okay, so we can say that the observable in the observer pattern is the producer of a sub-event, and the consumer is and the observer is somebody who learns about the event and so is consuming the event. Okay. Similarly, in the wait notify situation, the unblocked thread gets to know that the condition to proceed is true now, so they learn some piece of information. Okay, so they are the consumer, and the notifier is the producer. Okay. After the notifications occurred in the observer pattern, the observer can go and call some getters in the observable to learn more information. Okay. So while you can pass information to all the information that the observer needs in the notification, each observer might need different amounts of information, and sending all the information to everybody may be inefficient, especially if it's in a distributed context. Okay, so you can allow each observer to pull the information that it needs. In fact, in the original Smalltalk model, there were two such methods: one that took no argument, one notification method that took an argument, and the argument method was an afterthought. And initially the whole idea was that, and that was not designed for a distributed system, that you would go and invoke some getter to get more information. Okay. My animations went a little bit out of order here. And observer and observable are separate objects. In the wait notify case, again, the unblocked waiter can invoke additional methods in relevant objects. Okay, the synchronizing object, for the monitor, for instance, to learn more event information stored by the producer. Okay, so there's a similarity there. And observer and observables are separate objects. Notify and unblocker are separate threads. So in both cases, we're talking of separation. In one case, separation of concerns. In one case, we are separating the concerns in different objects. In the other case, we are separating the concerns in different threads, which may execute code in the same object, but ideally are executing code in different objects. Okay, so that's a similarity. Lots of similarities. Okay, there was the many-to-one and one-to-one relationship mentioned. So even in the thread coordination case, we have notify all. Okay, and it is possible that one event may ultimately through series of connected events result in multiple people being notified about the same event. Okay, but notify all does exist, and when I meant notify, I meant both notify and notify all. Okay, so that's actually that holds true in both cases. Okay, so an observable can be associated with multiple observables. Okay, and a notifier can unblock multiple waiters, which can be unblocked by multiple notifiers. And so it goes two ways. An observable can have multiple observers. An observer can go and get events from multiple observables. Similarly, in the thread case, a producer can pass information to multiple consumers, and a consumer can get information from multiple producers. Okay, so the one-to-many and many-to-many relationships exist in both cases. Okay. So, what is the difference? And this is something the students often get confused by. Okay, in the observer pattern, they sometimes think that there are two different threads executing the observable and observer code. So there's only one thread that is executing methods in the observer pattern. It's jumping between objects. Okay, it goes from the observable to one observer, then another observer, then another observer, then it comes back to the observable. But it's only one thread. Whereas unblocked waiter and notifier are separate threads. Okay, so that's the fundamental difference. The notify method in the observer pattern takes an argument. Even though I said in small talk, the initial notify method did not take an argument, but the basic structure is such that you can pass when you can pass 0 arguments, you can pass multiple arguments to a method too. Whereas the unblocked thread in the process coordination case gets only one bit of information, that the condition it was waiting for is true now, or may be true in the hint approach. The notify method takes no argument. No information is being sent through the notify method. It's indirectly sent by unblocking a wait. Okay. So let's use a graphic to illustrate the similarity and the differences. So on the top you see the MVC pattern, observer pattern. On the bottom you see the thread coordination. So let's look at the observer pattern. There's a particular thread, just one thread involved. Every thread is associated with a root method. In Java, that can be the main method or a run method. Okay, and the observable has some state, and the observer is interested in changes to the state. Okay, in the process coordination cases, there's multiple threads involved, and there's an object that is mediating between among the threads. And when that object has got synchronized methods and wait and notify, it's called a monitor. Okay, that monitor can have state. Okay, so there is state in both cases. Okay, state that can be changed, and it is changes to the state that are communicated to the consumers. So in the observer case, you do some kind of write. You change the observable, and the observable. And in the case of the concurrent case, you do a write to the monitor to change its state. Okay, so the observable goes and calls notify in the observer. So I'm assuming just in the remaining discussion, I'm going to assume only one observer. Okay, my pictures will get very cluttered if I assume multiple. Okay, so without loss of generality, the concept will apply to multiple observers. So you directly call the notify method in the observer. So the code that is going to consume and process that information is called directly by the producing code. They're in the same stack, the same thread. Okay. Here you do a notify. Okay. So with no arguments. Somebody who has been waiting for this information gets unblocked. Okay. And can then go and consume information. Okay. So if you want more than that one bit of information, you have to make a read call. Whereas in the observer pattern, you didn't have to make a read call. Okay. So multiple threads, single thread, And you see the similarities, you see the differences here. Okay. And sorry, actually I do have multiple observers here. So you can have multiple observers here, and you can have multiple threads that go and read information on the same monitor. Okay. You can have multiple observables passing information to observers. You can have multiple threads that go and write information and notify in a monitor. Okay, so I do actually allow the many relationship here, but later I'm going to just show you only one observer and one observer. Okay. Okay, so that's interesting. It's always I love to go and integrate concepts because I understand things at a high level of abstraction. But is there any practical benefit of doing this integration? Would we change the way we code? Would we change the way we code rather than just understand what we are doing better? Okay? And we would change the way we code if we would somehow go and combine elements of the both patterns. Okay? So my specific question to you, which we'll discuss next, is does it make sense to replace or augment, sorry I put an R there, or augment the observer notify with a monitor notify? Are they two alternatives to the same that can be used in the same problem, or are they totally meant for totally different problems and I'm just trying to combine them in some artificial way? Okay. So that's the question, and I'll let you guys answer. So in fact what UG said is exactly what I was aiming for. And let's look at the real problem, why we might need concurrency. Okay, so UG said that we can get concurrency, and why do we need the concurrency? So let's look at the situation when things are well behaved. Okay, so a thread writes information to an observable, notify occurs to one observer, and notify occurs another observer. It writes another piece of information, another notification occurs in each observer. Things are going well. Okay, but as UG mentioned, the observable has to wait for the notify method to return before it calls another notify method. Okay, and UG said, look, why not go and do them concurrently? And what would you gain by doing them concurrently? Let's say the notifying an observer is really slow, or it's in an infinite loop. Okay, there's no way. Remember, this is an up call. The observable can't control what the observer is doing. That's the whole point. The observable is supposed to be oblivious of what the observers do. Okay, so if that notification is slow, or if it never returns, the other observer will never get the notification, and the observable is blocked, and so he'll never get a chance to write again. So here we have an observer in a lower layer that is supposed to be oblivious to the observables, and its work is being impacted. Its ability to go further is being impacted by the observer. Okay, and so there's no new write, there's no new notification sent to anybody. So what role can multiple threads and monitor notify play here? I mean, this is the problem we're trying to solve. So towards thread-based observer pattern, so the general question we're trying to answer is, does it make sense to integrate the notion of thread coordination observer pattern? And as Jason mentioned, so the idea is to execute notification methods in separate threads, and there's two ways possible. One is all notifications occur in one thread that is separate from the one that is made the causing change. Okay, so one observer can affect other observers, but an observer can't affect the observable. Okay, threads are expensive, by the way. Okay, and the other approach is Jason's approach, which is the most flexible, that have a separate thread for each observer. Okay, and now without loss of generality, I'm going to assume one observer and one observer. Okay, just because my picture will get cluttered otherwise. So this is what we can do then. We now have a thread that is making changes to the observable. So it's now a producer thread. And there's another thread that's reacting to changes by executing appropriate changes in the observer. So that is now a consumer thread. Okay, so now the observable is a producer object and the observer is a consumer object in the observer pattern. And we also now have producer and consumer threads. So we've combined these two concepts together. Okay, not in some artificial way, but in a real way to solve a real problem. Okay. So when the thread that is writing when a thread needs to write, it writes to the observable, not to the monitor directly, because we still expect that and the observable might be the monitor, but the object is writing to is the observable. Okay, and that may itself be a monitor, or it might have an external monitor, and it goes and writes the information in some state in the monitor. Okay, so that state gets stored in the monitor, and the information is being read by the consuming thread. Okay, so it reads information from the monitor, and in the meantime, while it's and so after reading the information on the monitor, it should go and call the notify method in the observer pattern, right? But these two actions can occur concurrently. So before it is called the notify method in the observer, the second write can occur, and notify can occur in the observer concurrently or interleaved. Okay, so we have concurrency here, and we see here that the writer is not waiting for the notify method to finish execution. It can proceed earlier. Okay, so you guys get the point, basic point here. So the second write can then go and rewrite another event, okay, which can be read again. Okay, this is the structure I've given you. I'm going to spend almost all of today and a lot of Tuesday getting this right. There's lots of problems the way I have coded the problem so far. Okay, so let's go and solve these problems one by one. Okay, so I show you here two writes and two notifies, and each notify corresponds to a particular write. Okay, and that will work well if these two threads execute in some order and invoke methods in a certain order. But we aren't guaranteed order in threads. We aren't guaranteed any pace in threads. So let's look at the first problem, that the consumer is much faster than the producer. And the question is, what problem can occur if this is the case? Okay, so that's what we'll discuss next. So David pretty much explained the problem we have, that the consumer may do the read call before the event it needs has really been produced. Okay, so he said it's busy waiting for it. Actually, it doesn't do any wait at all. Okay, so the producer does a write. That event gets written. Okay, and let's say that event gets read also. And after doing a notification, the producer is slow, the consumer is fast. It makes the second read call before the second write call has been made. Okay, it's going to read the same event again. Okay, so that's a very concrete problem with this particular semantics. Okay, so it gets notification of the same event multiple times. Okay. Concurrency creates all kinds of problems. Okay, and I once asked an industrial alumnus of ours, what are the biggest sources of bugs in industrial code? And he gave me three conditions, two of which I remember. One is user interface code. You can never anticipate all the mistakes a user will make. And second is concurrent code. Okay, that causes all kinds of bugs. and I forget the third one, or maybe he didn't have a third reason. Okay. So the write is now delayed. It goes and tries to write later, and the second read should have returned this event, but it returned the first event. Okay. So now the next question is, David said that it's busy waiting. No, the problem was not waiting. So the question is, we need a wait call now. We need to use this red object as a monitor rather than just as a monitor with wait and notify rather than just something with synchronized methods. Okay. So how do we slow down the consumer exactly? Okay. How do we exactly? What is the exact? How do we make the wait and notify calls, and where do we make them? Okay. And the purpose is to slow down the consumer to make sure that this problem doesn't occur that I've just showed you. Okay, so what's your name? Nolan? Okay. Okay. I've learned 3 new names today. So we have to slow down the consumer. That means it's thread 2 that must be making a wait call, as Nolan pointed out. Okay. So as Leo mentioned, we need some variable. He was saying number of events. We are just trying to make sure that we don't, we can just have a Boolean. And that Boolean says whether there is an event produced or not. So we'll say while not produced, okay, or while number of events is 0. Okay, that's another way, but we don't need an integer. We can just keep a Boolean. We wait. Okay, if we're doing a wait, somebody must do a notify later. And the writer goes and writes the event, and then makes the variable true. Remember that the thread 2 is waiting on a particular Boolean, and that Boolean should change a state if it's going to proceed, just in a while loop, and it does, and so the produce becomes true. Okay, so the coordinator monitor not only has state for the event, but it also has state to coordinate. Okay, the produced variable, and it does a notify. And this point, the wait unblocks. It reads the event. Okay. We want to make sure that that the next person, if it calls this code again, the consumer, it should block, right? Because it just unblocked. It consumed it. It may come right back and execute this code again after notify. So we have to slow it down. So this is our way of slowing it down. We go and say produce equals false. It will become true when the next event is created. Okay, so if produce is going to become true someplace, it's going to become false someplace too. So we make it false here, and so it becomes false, and we call notify. And if we now come back to our loop before another event has been produced, produced will be false, and we will block. Okay, so that's the exact kind of code I was looking for. Okay. Now let's talk of the problem. What happens if you have a faster producer? Okay, and the solution should be kind of symmetric. So okay, faster producer. So as John Ray, more or less pronounced it right, said is symmetric. Okay, and he pretty much gave us the whole code. Okay, except he kept using the word we, but from context it was very clear which thread he meant. So thread 1 does a write, and so this is the problem first. Okay, so it goes and writes E1 and sets produce to true. That becomes true here. It does a notify, and it does another write, and E2 will replace E1, and when the consumer will then get E2 and it will have missed E1. That's a problem. I haven't told you the solution here, and so this producer is slowed down, but the consumers slowed down. The producer is not, and we missed one notification. We missed E1. We just got E2. If we don't slow down the producer, okay, that's the reason for slowing down the producer. So how to slow down? Okay, we have while produced, the consumer does while not produced wait, the producer does while not consumed wait. Okay, so the way I named the variables, it allowed for an easy symmetric solution. If I just named it var1, var2, we won't be able to sort of that easily translate one to the other. Okay, it writes the event, and then it wants to make sure it has written the event, so it wants to make sure that produced is true, so that the producer can go and unblock. Okay, it wants to also make sure that if it comes back immediately, it should block. Okay, so it makes consumed equal to false. Okay, so produced equals true unblocks the consumer, and consumed equal to false, assigned false, make sure that it blocks if it comes back too quickly. Okay, and if you and this is the most subtle part of the whole discussion. Okay, those of you who looked at the queue-based solutions, the same concept applies there too, except that we're applying it to a queue, which is kind of simple. Okay, so this is the complicated part, and it does a notify. At this point, the consumer can read the event. It has to now make sure that if there's a producer blocked, it can unblock. So it goes and sets consumed equal to true. It has to make sure that it blocks next if it comes back too quickly. So it makes produced false. And it notifies any waiting producer, so that it can indeed unblock. Okay? This is it. This is the most complicated synchronization you will see in this class. Okay, and if you've understood this, you're good. Okay. So if another write comes in, it'll write the new event. It won't block because consumed happens to be the right value. Okay. And so this notification will be received by. So both notifications are received by the observer. Okay. Okay. Now we have to look at any additional problems. Okay. A lot of you guys have been itching with certain solutions, but you'll have to motivate those solutions for me. So this is my solution. Okay. This is not something you've studied in operating systems. Exactly. Okay. So, but from operating systems, you guys have learned certain solutions. And so, but I want the problem. I want to know why this hammer you're thinking about is appropriate for this context. So tell me what problems are remaining to warrant a more complicated solution. So let's go back to what the problem you were trying to solve. Okay, so Brian, right?
Yes.
Okay, so as Brian put it, we were looking at the situation where notify doesn't return or takes a long time. And what happened in the single thread case was that the producing component just had to wait, and we couldn't do any more production. It's the exact same problem we're going to have now, maybe delayed by a couple of events. Okay. So if notify in an observer may be slow or does not return, okay, the producer will not be able to do any more writes. Okay, so after doing these two events, if the third notify is slow, and this producer does a write, it will just block, and it will never be able to produce event 3. Okay, so we follow two events, and we assume they went fine, but the third event is never going to be delivered because that third notify had some took some state that made the observer block. Okay, so that is a fundamental problem with this solution. That is why we need the hammer you guys were thinking about. Okay, and how can we solve the problem? Here's a solution, and I'm going to argue this is a good solution. Just don't make the producer wait. Let there be data loss. A problem that Leo said was bad, I'm just going to say, it's not so bad in certain situations. We just won't make the producer wait. Okay? And that actually happens in your computer system. When you have a device talking to the CPU, okay, and if one is slower than the other. Okay. So let's say the device can't keep up with the CPU, or more importantly, let's say the CPU can't keep up with the device. So network card is pumping data in, and the CPU is slow. The device can't be made to wait. What does it mean to make the network card wait? I mean, there's information coming in. It can't go in, just stop the information from coming in. So in general, devices and CPUs talk through device registers. Those device registers are not a queue. They are one piece of data. Okay, and if the device register is not consumed, you either get an error or you overwrite the previous value. Okay, so this is exactly what happens, and it's not a bad solution. Okay, ultimately, if the producer is going to block, maybe after one event or maybe after 10 events, it is going to block. So the consumer can affect the producer. Even in your queue-based solution that you guys are thinking of, the producer can be slowed down. It will be a little bit more efficient than the solution we had, but it's not going to be perfectly efficient. Okay, so so external device does not wait for CPU to consume data from device registers, which we'll probably learn later. When we talk about non-blocking I/O, the non-blocking I/O is very similar to interrupt-based I/O in computer systems, and I'll try to show the connection between the two. Okay, but that's when one agent can't wait. When somebody can wait, can be reduced rather than eliminate producer waiting. Okay, and you guys and what I've said earlier have already hinted at having a queue. Okay, I'd lost track of the time again. I'm glad I just saw it. We will just go and buffer the events, something that you guys have been itching to do. Okay, so we now don't have one event variable. We have an events variable in the central object, in the monitor. And when we do a write, and that write is not going to do a write of some state, it's going to do a put in a queue. Okay, we're going to call the operation that adds to the queue as put. Okay, and that's going to put this event in there. And if you do another write without having that event be consumed, you go and just put another element in the queue. Okay, and then the queue can be drained at the rate it is drained. That's possible for the consumer, and so it can go and get the first event, and it can get the second event. Okay, so queue is something you guys have learned in a data structure class. You don't have to, you needn't have gone to an operating system class to think of queues. Okay, so so we have to figure out what the problem is with using an ordinary queue. Why do we have to go and study these queues again in operating systems? So so we have a queue solution, and now my question to you is, what's wrong with this solution if we just use the queue you implemented in data structures? Okay. So there were really two problems. One, Adit, what Adit said was that normal queue is not thread safe, so we can easily make the get and put operation synchronized. That's an easy problem. Okay, queues are not fair. That's actually, as long as it's not a priority queue, the queue will be fair. Okay, it won't lead to starvation. So the problem is that we haven't. What happens if the queue is full or empty, and we haven't taken care of the fact that there can be a fast producer or a fast consumer. We haven't talked of waiting and notifying. So we somehow need queues that have both synchronized methods, have got asynchronous methods, and synchronized methods have wait and notify in them. Okay, so that's what we need next. So the next challenge is how to go and implement such a queue. Okay, and what we need is what we'll call a blocking queue. Okay, a queue that will block you if somebody else is already in it, is executing something in it, and it'll block you if your condition to proceed is not true. Okay, so we need to somehow implement a blocking queue. The blocking queue will be just like an ordinary queue. It'll have events, but it'll have some extra variables that are put in there that will help you synchronize the producer and consumer. Okay, what are those variables? That answer is actually quite simple now. Now that we've done that we've essentially seen a queue of size 1 already, and when we have a bigger queue it actually simplifies the problem somewhat. Okay, so that is something we'll leave to next time. Okay, and till Tuesday. But in your assignment that I'll give you, I'll ask you to go and use the blocking queue that Java provides, and you will see that, and you see through the discussion we've had today why you need such a queue. Okay. So what we'll do next when we come back is how to create an array-based blocking queue, so that you actually understand it, how it works. You'll be just using it in the assignment. You'll understand how it works. Okay, and you meaning the people who have not done OS. The ones who have done OS have seen this in great depth, but it'll be good for you to understand again what's really going on. Okay. So last time we looked at the producer-consumer problem, and normally that problem is cast as a multi-thread problem, but I cast it as a single-thread problem and said even in single-thread applications, we might have a one component producing information, other component consuming. Okay. And the example I took was a pattern that we are familiar with in this course and in earlier courses, which is the observer pattern. And we saw that an observer is really a consumer of information that the observable produces. Okay. And in the single thread implementation, the problem was that one observer could hold up the observable's actions and the notifications to the other observers. Okay. So if one particular observer is slow or has a loop that doesn't end in the notify method, nobody else will get notifications and the observable or the production of information will not continue. Okay. So we went through many solutions to try to solve this. And in all of them, we had multiple threads. Okay, so this is a multi-thread observer pattern, or which is actually it's more general than the observer pattern. But here I've shown you its application in the observer pattern. So we have one thread that's producing information, and we have another thread that's consuming information. And the observer-specific functionality here is that the thread that's consuming data that the producer has produced goes and calls a notify method in the observer. Okay, so which is of course a well-defined notification. It's a notification method. Okay. And the solution we wanted was a queue of items where the queue has the items are the produced items. Okay, so the producer goes and adds to the queue, and the consumer removes from the queue. Okay, so we have put and get essentially, and we explained this in very abstract terms last time. We didn't exactly explain how the queue would be a monitor and how the queue would function. So that's what we're going to look at today. And hopefully we'll end the discussion today. So the question is how to create, this queue is going to be a blocking queue. It's going to have synchronization built in. And we're going to build the queue from an array. So the question is how to create an array-based blocking queue. And for those of you who've done operating systems, you might think of this as a simple problem once you've seen the solution. Even if you've seen the solution, I've taught graduate operating systems for many, many, many years. And I've given this problem as an exam question, and almost nobody has got the solution right. Okay? They always have some problem or the other. So this is a harder problem than it might appear. So let's go through the solution, especially for those of you who haven't done operating systems. And one way to go and sort of figure out how this blocking queue should be implemented is to assume the data structure view of queues and then go from there to a blocking queue. I'm going to take even simpler steps. Okay, in CS1 when I've taught in CS1 I've taught arrays in the context of a history. A history is just a collection of items where you can only add items to it. Okay, so we study histories in CS1, and we're going to start with my solution in CS1, and then we'll try to migrate to evolve it to a blocking queue. Okay, so we'll go first to a just non-blocking queue, and then we'll go to a blocking queue. Okay, so three steps. And here's how you do a variable size history with arrays. Arrays by themselves are not variable size; they're fixed size. So what we'll do is we'll assume that the array consists of a bunch of filled items followed by a bunch of unfilled items. Okay, so there's a maximum size and there's a filled part, which is the size of the history, and then the unfilled part is derived from that. Okay, and something happened when I transferred the slides to this computer, but I had actually a measuring cup here. Okay, and then a measuring cup has an upper limit, so that is that like the measuring cup size, and measuring cup has marks that indicate how much you have filled. Okay, so that would correspond to the filled part and the unfilled part. Okay, somehow my images have just disappeared, but I'll try to fill them up later. But you can use your imagination here. Okay, so we don't just have an array now. We add another data structure, which is a pointer that indicates how much we've filled. Okay, remember the filled parts are followed by the unfilled parts. So we just need to know where the boundary is. Like in the measuring cup, we need to know till what spot we have filled. Okay, and whenever you do an add, we just bump up the pointer, and before that we go and add the new element at the pointer position. Okay, so the pointer is telling us where in the array the next element will go. Okay, so this is, like I said, CS1 material. And what we have then is an example of a bounded dynamic collection. Okay, and so dynamic and variable size are both the same terms. I should have used one and not the other. But basically, we'll say that a collection is a group of ordered to unordered objects of the same type. Okay, so a set is a collection, and an array is a collection, and it's variable or sized or dynamic if the size can vary. Okay, so whenever you have a bounded dynamic collection, you want to know whether the collection is full or empty. Okay, that's a question we'll have to answer in the context of queues. There it'll be a little complicated. And this is also a question we need to answer in the context of our history. Okay, and here it's not. And the next question we have to do is when we have a concurrency, or even when we don't have concurrency, what to do when an add or remove is emptied on a full or empty dynamic collection. Okay, in history there's no remove, but in Q there will be a remove also. So these are the two questions we need to answer. And for any collection, that is. How do we know that a bounded dynamic history is empty or full? This is where the answer is simple. So if next n is 0, we are to the very first element, then it's empty. Okay, and if next n is array.length, then it's full. Okay, so this is the simple part. So we've done the first part here. Okay, now comes the more interesting parts. So the next question is, we want now not a history but a queue. We don't want an add, we want a put. That's what an add operation will be called. And we also have a remove, which is going to be our get operation. Okay, so how do we go from a history with an add operation to a queue with a put and get operation? Okay, where the queue semantics are first in, first out. Okay. So the first question I'm going to pose for you guys is that I have an array and next in. We are going to still use an array. So tell me, what data structures do we need besides an array for an array-based queue? Okay. So I named it next in, and if you're going to have something to remove, then it makes sense to have a next out pointer also. Okay. So next in is like our history add. It adds element at next in and increments it, and our get uses next out. It reads the element at next out and then increments next out. Okay, so that was relatively straightforward, and so this is so what happens now? Okay, my pointer was at the last element of the array, and I added an element to that last element. Okay, and where should my pointer next in be now? Okay, my next out is at Jodo, okay, which is the first element of the array if 0 is the first element, which is the, if z is the second element of the array element, the element at position 1. And I just added an element at the last slot in the array. So where should my next in be now? So it should wrap around, okay? And next in comes right here, okay? So we have logically a circular bounded buffer, okay? And if I knew how to draw circular bounded buffers, I'd draw them here. Kevin does, so I'll show you his slide at the end after I finish my discussion, okay? So, okay, so we now have a bounded queue. And now the question is, how do we know a bounded queue is empty or full? Okay. So, and what to do when an add or remove is attempted on an empty or full queue respectively. So how do we know a bounded queue is empty or full? So let's assume this is a queue state. Next in is a James Dean and next out is at Joe Doe. Okay. Let's say that we do a bunch of next outs so that we consume Joe Doe, Jane Smith, Jane Doe, Mary Dean, and we are at Jan Dean now. Okay. So we've consumed all the items other than James Dean. Okay. So if we go and consume Jan Dean, then we will be at James Dean. Sorry. We had consumed James Dean was the next out, next in position, so James Dean was not in the array. It's just there from previous writing. Okay, so we had consumed all the items other than Jan Dean, and now we are at position 0. Okay, they're both equal. They also happen to be in the beginning, which is just a coincidence. Okay, so we know at this point the queue is empty. Okay, all you guys said that, look, when the two pointers are at the same position, the queue is empty. Okay, agreed. Okay, and yet I told you grad students get this wrong. Okay, so and you guys have pretty much got the right solution, but I have a little bit more to say about that. Now let's assume again the original queue state that next in is a James Dean, okay, and next out is a Joe Doe. Okay. And now we don't go in, and so we haven't consumed Joe Doe or any of the elements after that, okay, in the queue. And now we don't increment next out, we increment next in. Okay, so we have a new item to add. Okay, so we do have an empty slot here, right? We can write at James Dean. That is the next in position. That position is free for us to write. That is why next in points there. Queue is not full right now. Okay, there is an empty slot left. Yet next in plus 1 mod buffer size does equal next out. Okay, so the queue is not full, even though the condition that you guys said for the queue full applies here, but the queue is not really full. Okay, it will be full if I actually go and advance next in, and at this point again there will be. Okay, so given our data structures, there is no way to tell between the full and empty conditions. Okay, so the solutions that have been proposed all say let's keep some more state. Okay, and what John Ray suggested was was 2 ways of keeping state. And what Chris suggested was a third way of keeping state, remembering what was the last operation done. Okay, so and here's the counter solution that you talked about. So we'll go and add. We'll create a new data structure called size. Okay, which indicates how many items there are. And when it's empty, size is 0. And when it's full, size happens to be the length of the array. Okay, so even though they are both pointing, in both cases we are pointing to the same, the next in is equal to next out, size can distinguish between the two. So our queue empty is size equals 0, and a queue full is, condition is size equals array dot length. And the other solution is, again, what somebody explained, that we intentionally leave one slot empty. Okay? So just before the queue gets full, we know that next in plus one mod size is going to be next out. Okay, so we don't fill in the last element. Okay, again, we are keeping two data structures and one slot. We are again wasting one data item, one slot. Okay, if your buffer is very large, it's better to have a counter. If your buffer is an int, like in my case, they might as well have a size. Okay, so so solution 2, we keep one empty slot and use only array length minus one items. Declare it full when only one free slot left. Okay, and like I said, if the buffer happens to be a large element, it's not just a pointer. If it happens to be some kind of struct in C, that's a large item. Then the size solution is better. And I personally like the size solution. I find it easier to code. Okay. So this is the condition then for the case when we keep one slot empty. And now I'm going to show you Kevin's slide in a circular buffer, which assumes one slot empty. So by the way, Kevin is the one who taught me PowerPoint. And believe it or not, before you guys were born, there was a time when we didn't use PowerPoints, and I didn't use PowerPoint. And he got on my case, and I got on my case, and I finally started using PowerPoint. I used to use a tool called iDraw, which was this package from Stanford. And so it's not surprising he's ahead of me in PowerPoint. So we've got a circular queue. I don't know how he drew it. Okay. And here's next out. Here's next in. Queue is empty. And the red items are the ones that are filled. And next in advanced. It advanced some more. And now next out starts advancing. Okay. And we don't use up this element. Next, okay. And now we do consume an element. And next in now is empty again. So we're not at position 0. We're at position 3, but it's empty. Okay. And we start adding elements. And we add some more. We add some more. And we do not add an element at the last slot left. Okay. So at this point, we declare it full. Okay. Okay. So we know how to do an array-based queue. Okay. And let's talk about doing an array-based blocking queue. Okay. So we know how, we figured out how to determine if a bounded queue is empty or full. And the question now is what to do when an add or remove is attempted on an empty or full queue respectively. And we're talking now a concurrent situation. And we have the ability to block. Okay. So the question is, when do we block and who blocks? Okay. So we're going to assume monitors. Okay. So in operating systems, you probably did things with busy waiting, semaphores, and finally went to monitors. We are just trying to figure out how to program in a high-level language right now. So we're trying to understand how Java works. Okay. Java has monitors. So we will assume monitors. Okay? And this will help you understand what to do in assignment 2 or how assignment 2 is working. So for a blocking queue, we need to first allow multiple threads. And we want to make our operations both get and put synchronized. So that because they are changing a queue. Okay? And there's many operations there. We don't want to do some operations and not others. Okay? And it's not enough to just block you on entry. It's also important to block you if the precondition for your operation is not met. Okay? And the precondition for a get is that there should be an element to get. If there is no element, we have two solutions. I said Java. Java has hints. What UG gave was the solution for the hint solution, but let's consider both the hint and the absolute solution. Okay? So in the absolute solution, we don't need a while. We just do an if, and we are saying if it's empty, then the get waits. Okay, and it does the bookkeeping that I talked about. I've left the exact bookkeeping details out here. I just say inc next out and inc next in, and who knows what that does. It can either just change next in and next out, or it can also change size. Okay, and I've left is empty and is full also undefined, and it can check size or it can check the next in and next out elements. Okay, so so you do a wait on if it's empty, and you meaning get does a wait if the buffer is empty, and conversely put precondition is that the buffer is not full. So the buffer is full, it does a wait. Okay, so doing the wait makes sense, and each party can go and make the precondition for the other party true. Okay, so if the consumer is blocked on a get, then a producer can produce an item and make its conditional proceeding true. So since each of them can go and unblock the other, they both go in after they've successfully done their operations, do a notify. Okay, so pretty much the solution that UG explained. Okay. So that's our absolute semantics solution, and our hint solution is a while. And UG mentioned that we would do a notify all with the hint solution, and indeed you can do a notify all with the hint solution, but there's no reason to do a notify all. We know that when an item, only one of the threads can really proceed when we do a notify. So we might as well do when we've done our operation, only one other thread can proceed. Okay, so if the buffer was empty and the producer has produced one item, only one other consumer can actually consume that item. Multiple consumers can't, unless the consumers are all going and consuming the same item, which is not what we're assuming. Okay, so we're going to do more efficient notify operation, even though notify all will work. Okay, so some solutions are more efficient than others, and that's an important thing. Okay, and let's trace that in more depth. Okay, looking at real code. And this real code, like I told you, I may feel more comfortable with size. So I've got the size solution here. And I had, again, an icon for lock. And that icon is no longer displaying. And I wonder what happened. This is a Windows 10 machine. I had it on a Windows 10 machine. But in between, I went to a Windows 8 machine. So who knows why my images have suddenly disappeared. Or it could be the PowerPoint versions too, right? So this is our code, and let's say a consumer comes in, consumer 1, and the consumer wants to do a get. Okay, so we've put a pointer at get to say it wants to do it. We don't know whether it's actually going to be allowed to execute or not. Okay, when the pointer is pointing to a line that is shaded, it means it's actually executing. Okay, so right now no line is shaded, so it wants to do a get, and it can do a get as long as the lock is not held. And we'll assume that the lock is currently free. So it goes and starts executing the code. And I guess my animations are a little bit off here because I'm showing a second pointer, but that's a producer. Okay, so that's the producer's new pointer. And the producer wants to get in. And the question is, can the producer get in or not? And no, because we have one line shaded. That means there's already a thread in there, so the producer cannot execute. If it's not going to execute, we have two solutions in general. As somebody suggested in a previous class, we just keep trying again and again. We can get some kind of error code back saying, sorry, you can't execute. And that's a polling solution. We really don't want that. So we don't really get an error code back. But what Java does is put the producer in a queue. Okay, and this is the entry queue. The queue that you get into when you cannot enter the monitor, not the queue you go into after you entered. Okay, so the producer goes into the entry queue, and let's say after this another consumer comes in. The consumer goes behind the producer in the entry queue. So now we have three pointers, but only one shaded line, because only one thread can be in the monitor at one time. Okay. So consumer goes in, checks the size, and does a wait. Okay. So it's got the lock, but it needs to do a wait. So it has to be put in a queue, and it's not going to be the entry queue. It's going to be the condition queue. And if it's going to be allowed to proceed later, it should release the lock so that somebody else can make its condition true. Okay. So it releases a lock and goes into the condition queue. Okay. So all three threads are in the queue right now. And on exit, the next, since it's left the monitor, on exit method, the entry queue is always examined, and the first thread in that queue is executed, which happens to be producer 1. So producer 1, and before waiting, the class invariant should be restored. Okay. And what is the class invariant? It's a condition that is true before and after each public method in the class is called. Okay. While you're executing a method, the certain conditions may not be true, but the condition that is always true before and after is called the class invariant. Okay. So it's very important that since the consumer will lose access to the monitor, which means will release the lock, which means somebody else will go and look at the monitor, the condition for their entry should be true. So before this particular thread does a wait, it's extremely important. This is, not only do you have to worry about while and ifs, but you have to worry that before a wait, you always restore the class invariant. Okay? And to understand, let's try to understand what class invariant is. So what exactly is the class invariant in this example? Let's try to understand that so that we know what rules to follow a little bit more concretely. So let's look at our code. When we go into a put or a get, we go and change 3 elements. We change the buffer, we change next in or next out, and we change size. Okay? If we don't do all 3 conditions, then the relationship between the buffer contents, the pointers, and size will not be the correct one. Okay? That after we have gone and added after we've added an element, we should increment size and bump up next out, next in. And after we've done a get, we should, and after we've put an element in the buffer. Okay, so we have to make sure that all 3 operations occur or none of these operations occur. Okay? That's the class invariant. So and I'm not exactly telling you how, you probably have the right condition there, but I haven't worked that part out. But basically the point is that they should be consistent with each other. Okay, and we can say that if after each put, the element that was put should be at the position next in was before put was called, and size should be 1 more than what the size was. Okay, that's the condition for put, and similarly we can give a condition for get. Okay. Okay. So let's go and say now that a producer enters now. Okay. So we figured out that a consumer went and exited, and now the producer enters, and because it was in the entry queue, and it's going to go and notify. So when it notifies, the consumer is eligible to execute. Okay, and the producer is in the monitor. Okay, so far what I've said applies to both the hinge solution and the absolute solution, and the third solution I'll be talking about. Okay, and the question now is, and the answers differ based on what we do, given that both consumer and the producer, both the signaled or the notified thread and the notifying thread are eligible to execute. The notifying thread is in the monitor. The notified thread is no longer in its queue, and it would love to get into the monitor. Okay. So the producer has not exited, and where does the consumer go next? Okay, and that may affect what the producer next. We actually talked about this in the synchronization deck, and you guys should really go and study that stuff before you start doing your assignment too, because you really understand it then. Okay, so one solution is that we put them both in the monitor, we let them both execute, they're both ready to execute, but then it's no longer a monitor. We're talking about synchronized methods, and that's not allowed. Okay, that would be great if you could allow this solution. Okay, and this violates the monitor definition. So we go and put the signal thread in entry queue, which is what was mentioned, and this is the absolute semantics. We can put the signal thread in entry queue, which would be the hint semantics. Okay, and that is not a solution that was proposed. So I'm looking at some bad solutions before we look at the good solution. Okay, one bad solution was we put them both in the monitor. That's no longer, it doesn't make the synchronized method synchronized. Now a solution is go and put the consumer in the entry queue. Okay, you guys all said urgent queue, or one person said urgent queue at least. So what if I go and put this consumer one in the entry queue? What would be wrong with that? Okay, so let's go and answer that question. So what's going to happen is consumer 2 will get the buffer first. Consumer 2 came after the consumer 1 had done the wait, and consumer 2 will get the buffer first. And this can happen again and again and again. Okay, when consumer 1 finally gets in, again and does a wait, another consumer 3 might come in and ahead of it. Okay, so whenever you're not fair, when you go and give things out of order, the person who suffers may never get it, and that condition is called starvation. That's what UG said. Okay, so this is starvation is possible, where you'll never be able to get. It's firstly not fair, and versus that particular thread may never get denied. Okay, so to solve the starvation problem, so that was sort of the half hint solution. That was not quite the hint solution, but halfway there. Okay, and I'm going to switch from the hint solution now to the absolute solution. Okay, and put the let the signal thread go immediately. Okay, and so the signaling thread must go somewhere, and for the similar reasons, we'll go and put it in its urgent queue rather than the entry queue. Okay, otherwise that signal thread may never get a chance to execute. Okay, if it gets behind somebody who came after it. So we saw the solution earlier. We go and put it in the urgent queue. We have to put it in some queue, and it has to re-enter back, and it should get precedence over the threads in the entry queue. So we put it in the urgent queue. So consumer 1 executes. Okay, and when you use the absolute semantics, we have another condition now. Before you do a signal, before you do a notify, you must restore the invariant, which actually happens to be the case here. Okay, but because you might be chucked out right after you go and do the notify, you better make sure that the invariant is true before you do the notify. In both the hint and the absolute semantics, you have to make sure that before the wait, you restore the invariant, which makes sense, right? If I'm going to leave this class and come back much later, I better make sure that I've gone and cleaned up the projectors and so forth. But here, when I'm enabling somebody else to go, I might suffer, I might be kicked out. So before I signal, I have to go and restore the invariant. Okay, that's an extra condition you have to put in the absolute semantics. Okay, and so now at this point, consumer 1 leaves, and producer 1 gets in. Okay, before consumer 2 gets in. So that's the absolute approach, and as UG mentioned, because we have only one queue, in the absolute approach also we need to do a while. here a while size rather than an if. But assuming we do that, we change the ifs to the whiles. Why do we want to go towards the hint solution? What's wrong with the solution? Assuming again we fix the problem of changing the if to a while. Okay. Why go towards the hint solution? Okay, so I guess so we look at what the producer does when the producer comes in. The producer comes in and just leaves, right? The producer did a notify, had not done the return. Right after notify, it's kicked out. Consumer does its task. Then the producer gets back the lock, and what does it do? Execute a return statement to leave. So we have, as Yuji mentioned, just an extra context switch. If you had just let the poor producer continue, it would have left anyway. And here you're going and kicking it out and bringing it back in so that it can leave. Okay? So we have an extra context switch, and that is expensive. Okay? So how do we solve the problem? So signaling process enters only to leave. Okay? We see that after notify, it did nothing else after that. So how can we solve the problem? When one solution, so this is an unnecessary context switch. One solution was to say, well, whenever you do a notify, that is an implicit return. You cannot do any actions after notify. Okay? So a single signal is allowed. You can't do multiple signals. Okay? So no statement allowed after signal. So you can't do, for instance, a notify and then a get. Okay? And you can't even do a notify and then do a return retval. Okay? You would instead do a notify and return retval, which will just kick you out. Okay? So in that case, the hint and the absolute semantics become pretty much the same. Okay? But then you've gone and reduced the flexibility. So this is how history went. People did the absolute semantics, then they did the solution, okay? And then Mesa came around from Xerox, and they did the hint approach. And the hint approach puts the signal thread doesn't go into the back of the entry queue as I mentioned earlier. It goes into an urgent queue at the back of the urgent queue, and in this case it happens to be the front also. And the signaling thread continues execution, and the signaling thread can then go and exit. Okay. So signal thread and urgent queue service before entry queue. Okay. And the problem here is that we do allow statements after notify, as opposed to the previous solution I talked about. Those statements can then violate the condition for on which the thread was blocked. Okay. So that is why it's called a hint now, and you must go and do a while loop. Okay. So you can, if you're allowed to do a notify, do some operation after notify, you might go and do a get. For instance, the same thread might go and do a get, and that would go and destroy the condition. So signaler may violate condition, or previously signal thread may violate it by the time some other thread gets in. Okay. So signal is a hint now. So now when the producer leaves, so now when signal thread is in urgent queue, not guaranteed state at signal time. So signal thread must recheck condition. So we don't do an if. Okay, we'll do a while. Okay, and we do a while here too. Okay, even if you have multiple queues for conditions, you do a while. Okay. And the basic philosophy here is that you make the usual case efficient and the other cases possible. Okay, so you have to do an extra check when you come back. You have to do a while. That means you have to do at least one more check after you come in. So so that's maybe a little bit of a lack of efficiency. But what we've really done is made the usual case good. that in the usual case, the signaler is not going to re-enter the monitor after notify. No, it's not going to execute other operations after notify. In the usual case, the absolute semantics is slower than the urgent semantics, and we made that efficient. And just in case the condition is violated, you do a while, so you are safe. Okay, that extra check just makes sure that in case the producer, in case signaling process does do some extra signaling thread does do some extra steps that violate the condition, we check it. Okay, so that's kind of the philosophy. Okay, so hint versus absolute programming. Rather than saying if not okay to proceed, you'd say while not okay to proceed. Okay, you've seen earlier. Okay, and as UG mentioned, the if and while are also needed if you are going to have only one condition queue. Okay, the absolute semantics were proposed always with multiple queues, and hint semantics have been proposed only with a single queue. They said if you're doing a while anyway, let's go and have one queue. Okay. Now, does this while become polling? I said earlier that you can always keep checking if you're getting the queue or not. That when you go and call a get or a put and it's going to block or be empty, we can get an exception, as was mentioned by one of the students. So what if we just get an exception saying, sorry, your condition for entry is not true. Okay, and you go and recheck that. You do some sleep and come back and recheck that. So essentially, you've gone and done a while rather than an if. Okay. Here also we're doing a while, but we are not getting an exception. We're doing a wait. My question is, are we getting the disadvantages of polling? What if, is it equivalent to going and saying, while not okay to proceed, sleep? So as John Ray said, only if you get a notify you check. And in most cases, that one notify will guarantee you execution. Okay, after notified, bad things wouldn't have happened. That is the usual case. And so you will do one extra check, and rather than in the sleep case, you might, depending on your sleep interval, you might end up doing multiple checks before your condition is true. Okay, so even though the code is structured like a polling solution, it's not really polling. Okay. Not polling, as each iteration has a wait, and a wait proceeds only after a notify, not after some time interval. Okay. And in the normal case, notify will actually leave the condition true. It will be very unusual that after the notify, between the time the notification occurred and the time you entered the monitor, something bad happened. Okay. And this particular solution, this while solution, allows many things. It allows only one condition queue. It also allows notify all. Okay, so you needn't have notify. You can do a notify all, in fact, and that's what we are seeing here. So I've replaced all notifies with notify alls. Okay, so if my urgent queue has got consumer 1 and consumer 2, so what happens with notify is that the urgent queue will now have all the signaled threads. Okay, and they will be ordered in the same order they were in the condition queue, and each of them will check their condition. Only one of them will proceed. So first signal thread finishes, and then the second signal thread comes in, and the second signal thread will back and do a wait. Actually, it should do a wait in the condition queue rather than in the urgent queue. So it'll go into the condition queue, in fact, and finally come back to the urgent queue. Okay. So hint versus absolute. Absolute applications provided information with absolute guarantee. Okay. So the hint versus absolute discussion goes beyond monitors. This happens in real life, and this happens in other situations too. Okay. That when you go and say something, it's most probably going to be true, or it is definitely going to be true. Okay, so any of these machine learning algorithms today, they're all probabilistic. Okay, with a high accuracy, with a high guarantee, the information will be true, but it may not be true. Okay, Think about your leaving from one location to another location. You leave a forwarding address at your original post office. Okay, that's probably going to be true, but you may move another time. Okay, and so what happens when somebody writes you a letter? It'll go to the wrong address. Okay, and the post office will go and then figure the deliverer will go and figure out that you are no longer at that address, and then maybe look up some central database and see where are you actually, which is an inefficient task to go and look up some some remote post office. And this happens also when there's process migration in distributed systems. Then when a process migrates, it leaves a forwarding address at the previous location, and then if a message goes to that, and if the process moves again, a message goes to the second host, and the host says, no, this process is no longer here. And at that point, we go through some broadcast mechanism, we look up some central server and go and give the right address. Okay, so so in hint, the application provided information that is likely to be true but can be checked. It's important to verify whether it's true or not. And like I said, the server is probably on machine M, and if the message bounces, check with some central authority at some cost. Okay, so the condition which you're waiting is probably true, but you must check. So you must have in the hint solution code to check truth. If check fails, operations are more expensive. The usual case is efficient. Unusual case is possible but not efficient. Okay, unusual cases you have to do another wait, which is possible. So servers do not move usually. Condition does not usually get violated. Okay. Oh, my animation is a little off. So so what have we done? Okay, we started with the single thread producer-consumer problem. Okay, we went then to a non-synchronizing multi-thread one-item producer-consumer problem. Okay, we had one item in which we went to a multi-threaded solution with one item that was not synchronized. Okay, with waits and notifies. Then we went to one item synchronized producer-consumer problem. And then we went to a non-synchronizing multi-thread queue producer-consumer problem. And finally, we went to a synchronizing multi-thread queue producer-consumer problem. Okay, so we went in gradual stages. Now, in operating system solutions, and probably my next animations are going to be also consistent with what I'm going to say right now. But let me give the whole thing right now, and we'll just skip the next slide then. Classically, what's done is that people just go from non-synchronizing multi-thread queue producer-consumer problem to a synchronizing multi-thread queue producer-consumer problem. That's what you study in operating systems. You say, assume there are two threads, they need to exchange information, assume they need a queue in between. Let's go and see how to make it a synchronizing queue. Okay. So what I've done is I've gone and started with a single-threaded producer-consumer problem and gone in gradual steps to the other. Okay. Why did I do that? Let me see what my next few slides. Okay. Today, people understand how bounded buffers work. Implementation of it is not a challenge. The challenge that exists, and the challenge I see with students who do my course, and even when I do coding myself, is that people don't quite understand when to use bounded buffers. Okay? So this is like the idea of indirection. Indirection is a fantastic idea in all systems, but people don't use it as often as they should. And every time they find a new way of using it, they say, oh, voila, fantastic. And so, for instance, the factory pattern is just an example of indirection. You don't go and instantiate directly, you go to another object that does the instantiation, just indirection. But it's not just indirection. Indirection is just not natural. Okay? Similarly, you come across many situations where it's calling for a bounded buffer problem, and people are not, and multi-threaded bounded buffer problem, and people are just using single threads. Okay? The observer pattern, I've argued, should be multi-threaded. You shouldn't allow an observer to go and block other observers. Yet it's presented as a single-threaded pattern. Okay? So, when you code, just be aware of this. And every time, this is the hammer you have. Okay? I told you earlier, guys, that when you were coming to the bounded buffer problem quickly, I said, don't use the hammer when it's not appropriate. But now I'm saying that this is a very good hammer. Do try it out every time, every opportunity you have, because it's a good hammer.